Hi there, welcome back. Welcome back to the channel. And we are now into the fourth video on the design and build of the DIY tube tester for that small selection of tubes that I normally find on my radios. I've had some time to work on this and I'm happy with where I've got so far. I've now started to see something that looks a little bit like a tube tester. Bigger than I expected. I'll warn you, bigger than I expected, but we'll get to that. I know some of you are following this quite attentively. I know at least one of you has already started building a prototype. So I really want to encourage that. The more we can develop together, the better. And let me show you what I've done so far, and I hope you enjoy it. Stick around. Is that starting to look like a tube tester? You tell me. Sort of. I've got all the meters that I think I need. We've got one measuring B+, and that adjustment on the right is the B+ adjustment. Same for B2+. Same for the negative V bias. There's a switch to activate the high voltage, to send it to the tube. That should be a push button, a momentary switch. At the moment it's just an on-off. I'll explain why in a minute. And then we've got our milliamp reading, which is measuring the anode current in this case, because at the moment what I've got this set up to do is to test an EL84 or a power tube. And the reason it's being set for that is because this is a proof of concept for now. I want to make sure everything works, and then I'll work out how to be able to adjust or change the settings for the different tubes. Now, as you can see here, the back looks like a rat's nest. But it's all going to be explained because I'm going to start from the beginning, which is the supply board. I built it, I tested it, I made some adjustments. As you can see, there's one hefty big capacitor over there, and there's actually a voltage regulator on that heatsink. That is actually for the heater supply. Now, I'll explain all these changes and why I made them, and hopefully you'll agree with me, and we'll take this one step at a time, because I then will show you the result of testing this on the, testing the EL84 on this tester. And we'll be probably in a good place to take it to the next step. But before we carry on, I just want to thank the sponsors of this video, PCBWay. Right now, they're in the middle of their 5th PCB design contest, and they're inviting you to join. If you have any project ideas, by all means participate. The prizes are really, really amazing. Have a look for yourself. You just go to their website, pcbway.com, look for the link to the contest and get cracking. And they'll also serve you well with any other needs you have, like CNC machining, 3D printing, anything else you need, they'll sort you out. Okay, let's start with the main board. This is the board that I had designed and built and tested. And I've got to tell you, this works very, very well. Very well indeed. I made actually just one change over here. If I recall correctly, it was this resistor between the pi filter, between these two capacitors. That I changed to 100 ohms. I had 390, that was obviously too high. The minute current starts flowing through, when you start getting some real current, like in the case of the EL84, it draws around 30 something, 40 milliamps. You start getting too high a drop here, and then the voltage that gets through is not enough to supply the reference and to give you that, to allow you to go up to 250 volts or so. So 100 ohms. Other than that, everything is fine. Now, what I decided to do a big change on was on the heater supply. And the way it is now is called precarious, very precarious. What I've got is the supply coming out of here. You've got your 6.3 volts or so AC. It's going through one diode, and then it goes to the filter capacitor, big filter capacitor, 10,000 microfarads at 50 volts. And you can't see it down there, but the schematic will make it clearer. It goes through a LM338. Now, why an LM338? Well, the LM338 is an adjustable voltage regulator, and it allows you to pass up to 5 amps of current. Now, obviously, it's got to have the suitable heatsink, but I wanted some leeway. The 317, or was it 337, I beg your pardon, is just a little bit too flimsy, up to 1.5 amps. When this thing starts up, it sometimes pulls quite a bit more current when the heaters first get supplied. So I decided to use the 338, a lot more robust. It's got all the usual protections over heat and over current. It just makes me feel a little bit more comfortable. I've got a trim pot here to adjust the voltage, and I've got the usual filter capacitor on the input and small capacitor on the output, and that's our heater supply, 6.3 volts. Now, how do you get 6.3 volts DC from 6.3 volts AC? You can't. Okay, you can't because the 338 needs about 3 volts between the output and the input. So if you've got 6.3 at the output, you need 9.3 at the input. And it's got to be 9.3 at the bottom of any ripple, which is not that easy to achieve. And if you look at, I'll actually link to a video done by Fez, where he describes how to build a supply, a DC heater supply from a normal 6.3 volt AC heater supply. And believe me, it's not as simple as it seems, okay? It is not as simple as it seems. So what you need is a little bit more voltage coming out of here, or rather from the heater supply. 6.3 volts just won't cut it. Now, fortunately, our transformer allows us to play with this. We have various windings here. We've got the 240, 220, 200. Now, because I've got a regulated DC, regulated high voltage supply, I can actually play with this, play with the input. Instead of using the 240, I can purposely use the 200 or the 220 so that I get a higher output. I get a higher secondary voltage. You can't go too far down, you can't put it at 150. You can't supply 240 volts to 150. It's going to do something really bad to your transformer. But you can certainly supply 240 volts to 220 winding. And what that gives you is what would normally be a pain in the ass. That gives you a higher than 6.3 volts heater output, which would normally be a problem. In this case, that's exactly what we want. Now, let's say that you cannot get that. Let's say you cannot play with this. There's one other thing you can do. You can actually add windings to your heater supply. So how would you do that? Well, you'd need to have a transformer that actually has space on the edge here to allow you to pass some windings through there. This would have to be, this is very thin wire. It needs to be a little bit thicker because you're going to have about 1 amp coming through there. But if you can get wire through there, you can wind a few turns on here, and you can actually add this to your heater winding to give you a few extra volts or a few hundred millivolts if that's all you need. I'll give you an example. I have wound two turns around here, okay? It's just 2 turns. There's 1 going there, 2 going there. The number of turns are the numbers that go through there. And I'm going to switch this on and show you what voltage we get per 2 turns. Now, if we look at the meter here, this is measuring the voltage across those 2 turns. And it's 0.37, call it 0.38 volts for 2 turns. Now, that might not seem much, but when you try to add another volt or 2 to your heater supply, that's probably going to work. This gives you 0.3, let's call it a third of a volt. It's a little bit more than that, but let's call it a third of a volt. If instead of 6.3 you wanted 7.3, you need another volt. So 2 turns times 3 would mean 6 turns would give you another volt. 12 turns would give you another 2 volts. Now that's probably going to be more than enough to give you enough AC voltage at the output of your heaters, all right? Because it's going to sum, you're going to sum that 2 volts or 1.5 volts, whatever you've added on there. You're going to put this, this winding in series with your heater output to add those voltages. Now it's got to be in the right phase, otherwise it subtracts, but it's a question of experimentation. You are just adding turns to that secondary to give you a higher output voltage on your heater supply. So that's the other way of doing it if you cannot use the 220 volt primary selection here to give you those extra few volts. So that's just a by the way. Let me switch this off while it's still safe. We don't want to play around with this live. And I don't need this, so I'm actually going to remove these windings because I don't want to tempt fate and have any mishaps. This was literally just put on here to show you what you can do if you really need to. Now remember, if you do that, you need to use fairly thick wire. It's got to have enough space to pass it through because there's a reason why your heater wires are fairly thick. It's the part of the transformer that actually passes quite a high current. Okay, let's carry on. What did I do with this? I decided to put this on the board, but before I show you that, let me show you the schematic for this section. Here's the schematic for the entire supply board. As I mentioned, no changes over here, no changes over here, no changes there. The only actual change is down here. And here's our 8 volts AC or 9 volts AC, whatever you get coming in here. You need about 8 volts AC to comfortably do what I've done here. The half-wave rectification means that you have quite a bit of ripple at this point. That's why there's a 10,000 microfarad capacitor, just to give you some really good filtering on here. And even then, you've got to be careful. You've got to make sure that on the bottom end of a ripple, it doesn't come below 8.3 volts DC over here, because you need a difference, 9.3 volts DC. This is 6.3, this has got to be 9.3 minimum. It can be higher, can't be lower. Okay, and this is just for input filtering. You don't really need this, but I like to put it in there. And then I've got my usual setup here where I adjust, or I can adjust the voltage coming out here with this resistor and this trimmer. This trimmer is going to stay in place. Once you've set it, you set it and forget it. And this is just the usual, textbook case of setting up the voltage for a 338. This flyback diode, this bypass diode here, is in the event that you switch off here and you've still got voltage on this capacitor. It discharges through there, so it doesn't discharge through your IC and damage it. And there's our 6.3 volts out. Now the trick was trying to get all this, in fact, all this onto one board. And you'll notice I've got these things over here. These are heat sinks, which to get them on the board, you've got to draw them in the schematic. And that gets fairly interesting. Let me show you what the board looks like. I've kept it to as close to the original as possible. And also I've kept it within 10 by 10 centimeters, which is the maximum size for the base price that PCBWay will build. You can build bigger, obviously, but then you get onto different pricing. So let me show you what the board looks like. And here we are. It looks pretty good. It actually looks pretty good. I'm very pleased with the way that I managed to fit this. I have kept this section very much the same. This over here has now got the heatsink vertically. This heatsink, I believe, is sufficient for the current draw and the heat that we're going to need to dissipate. I'll show you that when I build it. We'll test it and check the temperatures. I've been checking them there even without a heatsink, and it's not an issue. This one here, this is the LM338 to regulate the heater supply. This one actually can get quite hot depending on what input voltage. I've got 0.28 volts AC. I've got 8 volts AC coming in here, but if you had like 12 volts AC, you would get a big dissipation on here. So you've got to be careful. This is that huge capacitor over here. I've tried to adjust, move these around a bit. I gave these a little bit more space because they were a little bit tight. What else have I done here? I've made sure that I've kept the connection blocks uniform. They're all the same type, with the exception of this one. It's the same type, but it's a 3 connector one. Now I've got the input here, 8 volts AC, and I've got the output there, 6.3 volts DC. And I've got another output here which says 12 volts DC. I've taken this straight from the rectified 8 volts AC. I need that 12 volts DC to switch something on when I power this whole thing on. And I'll explain that when we get to the meters. You'll understand why. So this board, I believe, is ready to go. I'm going to order it. I'm going to wait till I get the board and actually test it before I put it on the share section of PCBWay's website, where anybody can just make their own. I don't want to risk putting it up on the share section and having you try to build something that may need some alteration when I do the build. You never know. So that's what we've got here. And what we basically end up with is a supply that's giving us 0 to 250 volts or so on B1 plus, 0 to 250 volts or so on B2 plus. B2 plus is always relative to B1 plus, as we explained before. So if I make this 200 volts, this thing can't go above 200 volts. If I make this 150, this won't go above 150. So there's always a limitation. This one is always lower than that one. Then we've got our AC volts in, I've got our heater voltage out, and I've got our bias out. I've done away with the bias maximum. I tried to power the meters from that. The minute you draw any sort of current from this bias supply, any real current, it just sinks. I mean, this thing is not a high current supply. Fortunately, the grids don't need high current. They need the voltage, adjustable. But I had to come up with another solution for the meters, which I'll show you now. Now, this may look like a mess, but there's definitely method in my madness if you give me a second to explain it. These 3 meters and their respective trim pots or adjustment potentiometers are for the B1+, B2+, and the negative grid bias adjustment. I decided to put them all on the right-hand side, and the reason for that is that if you are setting it, you are setting it and watching it immediately to the left. Okay, so it's ergonomics that come into play here. I've configured the meters for the respective ranges. Now, this one here is set to the 500 volt range. This one is set to the 500 volt range. This one here is measuring up to about 20 something volts. So it's configured to the 200 volt range. This thing goes from 500, 200, 20, and 2. The 200 volt range is what gives me 1 decimal point on at about 20 volts. Okay, so I've got this, these connections here. This has got to do with a specific meter. You've got to see what meter you get. But if you do set it to that range, you get 1 decimal point, and you have to short out these 2 pins, which is what I've done. So I'm getting a, tenths of a volt measurement resolution on here. The other thing to be careful about is the powering of this. That meter there, which I'll show you in a second, is actually for the anode current, and that is configured differently. But let me explain how I powered these. These things need 9 volts, and they need their voltage individualized. They need their supplies individualized. You can't just connect this to one 9 volt supply and expect it to work, because it depends on where you're measuring. It's sort of the reference ground has to be the same if you want to supply it from the same battery. Okay, let's call it a battery for now, which is what it is. So what I managed to do is I managed to supply these 2, this one and that one, which are measuring B1+ and B2+, referenced to the same ground. I've managed to supply them from one battery. This one here is actually measuring a positive voltage, but it's a negative voltage that it's looking at. So our ground on this meter is actually the minus V bias, and the positive of this meter measuring is the ground. So you can't use the same supply, so you need a separate supply. Okay, so that's battery number 2. Then we get to this guy, and this thing is measuring the current that flows through the anode. Now you've got to be careful with this. You can't just reference this to anything. This thing's floating, so the only way this would work would be a battery. There is another way, and the other way would be using these things, those DC to DC isolators. And the reason you're seeing this over here is that I tried it. There were actually 4 of them on here because I was supplying the meters individually, and it didn't work. I couldn't figure out why. I actually supplied this separately from my bench power supply. I wasn't even getting it from that board. But this thing was creating so much ripple backwards that it was actually starting oscillations on my board. It was really going nuts. So what was happening is the minute I started increasing the voltage and dropping the bias so that the current started to flow, these things were creating noise. It was going back into there, and it was causing this to go into oscillation. I've never seen anything like it. I did not expect it. Theoretically, this was completely separate from this board except the test points. So theoretically, I should not have had any effect, but it was having a really, really bad effect. And that really disappointed me. I tried all sorts of filtering, more filtering. I tried putting filter caps on the test pins over here and the supply points. I tried everything. It just would not work. Okay, but the reason for all that was I wanted to avoid batteries, right? I mean, these things are expensive and they're a pain in the butt to use. I mean, you're wasting stuff there, right? Then I realized this meter, these meters, actually draw 1 milliamp. Now that means that no matter how cheaply these batteries are, no matter what quality I use, they should last a very, very long time. I mean, even if I left it on most of the time. But I can't do that, really, can I? What I can do is I can create a separate little board and use a little relay like this. This is one of those Panasonic TQ2 relays. It's a 12-volt relay. Whoops, fortunately I've got that off. You can use any relay you want, provided, well, I'll tell you what you want. You want as few relays as possible to switch on 3 batteries when the power goes on to this thing, okay? So what I'm going to do is create a little board, and the battery ground will go straight to there, and the positive, the battery positive, will come to one of those switches, one of those contacts, and when this gets activated and it produces 12 volts as a result of my heater supply starting to work and rectify, this relay clicks on and it switches on. It switches the power through from the meter, from the battery to the meter. These are double pole, double throw. I can switch 2 batteries on with one of these, so I'll need 2 of them to switch on 3 batteries. All I need is these things. I can use any relay I want, provided that the switching is completely isolated one from the other, and provided that I can get the supply. This thing is 12 volts. I know I can get 12 volts from there, or close enough. You know, this thing will operate from about 9 volts onwards. I've tested it, actually from 8 volts DC upwards. So that'll be enough. But you can use any relay that you feel will be able to be sourced by the board. For example, you could use an AC relay that can be supplied by the 6 or 7 or 8 volts AC that's coming from your heater supply. The minute you switch on your transformer, the relay is activated, your batteries go on, your meters come on. You don't have to click anything, you don't have to switch anything, they just come on, okay? So that's what I'm going to do next. That's what I'm going to use these little things for. I haven't designed that little board yet. It's no big deal. It's a very, very simple thing. I probably will design a board, but I could probably just use a little Vero board or something like that. I've got to figure out where to put all this stuff, because as you can see, this thing is turning into as big a device as that which I said was the reason I didn't want a real tube tester for. It really is big. I need to find a way of making this a little bit more compact for my own satisfaction, because ultimately I want to put it somewhere up here, okay? It's not going to fit down here, believe me. I would have loved it, but it won't work. So this board at the moment is really just for test purposes, so that I can work out what the best layout's going to be. And once this is finalized, it will be pretty neat. These batteries will be down on the bottom. There will be quite a bit of space, because this won't be here at all. It's on the board. So there will be space for all this. I'm not too worried about space. I then will have to work out where the wiring goes, because it's got to be a lot neater than this. It's got to be very, very neat. Whenever you're working with lots of wires and you've got things like, 9-volt battery wires, you've got 200 and something volts over there, you could, 6.3 volts over here. You have to be very, very careful. You don't want shorts. You don't want necessarily to have them very close to each other so that they don't radiate to each other. Okay, there's a lot of care to be taken, but that's something that I worry about as a secondary step. Now, the other thing, the most important thing will be, this is an EL84. This is a 9-pin tube, which at the moment is wired for the EL84. And the reason that's the case is because you've got there's 1 not used, 2 is the grid, 3 is the cathode, that's going to ground over here. The 4 and 5 are heater wires, which are coming from here. See that? 6 is not used, 7 is the anode, and that's coming from here through that meter, through the ammeter, and it's coming from there. I'll explain that in a second. 8 is not used, 9 is the screen voltage. Just to show you what I've done here, the high supplies, there's ground, there's B1, B2, they are being metered over here, but then they're coming to this switch down here, there and there. And only when you switch this switch on, when you activate it, and it's going to be a push button, momentary push. The minute you release it, it goes off. That's probably what I'm planning to use. I've got one. This is it here. However, this thing is so stiff that when I put it on this board, every time I pushed it, this whole thing was moving. That's why I changed it. but I might still use that one. That then comes through to the actual tube. So you can set all the voltages here on the meters, and only when you've got those set do you actually push it to test the result on the tube. So yeah, okay, and once this is here, you've got to decide how to get these signals to the different pins on the tube. Now, as I said, you've got HV1, B1, you've got ground, you've got B2, which is screen voltage. Some tubes don't use screen voltage. You've got your bias. Most tubes will, okay? So you've got to put that to the respective pin. It's not always going to be the same as the L84. In fact, it's rarely going to be the same as the L84. The only one that's actually fairly common would be the heater wires. A lot of these Novell tubes are 4 and 5 as the heater wires, but not necessarily, they're not all like that. The 12AX7, 12AEU7, 12AT7, they use, if you're going to use 6.3 volts, you're going to use 9 and 4, and then 9 and 5. So you've got to be able to flip this around. You can't be soldering this all the time. And the other thing is, I'm going to have another tube socket for an 8-pin, because there are some of the tubes on these radios that I use that are those 8-pin, I can't remember what the term is, I can't remember what they're called anymore, but they're 8-pin. So again, it's going to be different. So I could use, 9 banana sockets, where you take these signals and plug them into respective pins, like a lot of the systems use, or I'm planning on using a socket. Best way to describe this is I've got up to 9 pins for the tube, and I've got 6 signals. 1, 2, 3, 4, 5, 6. So I could use 6 and 9, 15, okay? So I've got to use a 15-pin socket, and then I can have a plug. And on the plug, I do the respective shorts. So let's say that pin 1 to 6 are the inputs. 1 will be B+, 2 will be ground, 3 is B2+, 4 is that, 5 is that, 5 is that. Then I know that I've got to short on the plug, on the male plug, I've got to short 1, 2, whatever this is connected to, right? Or it's going to be pin, in this case for the L84, it'll be pin 7. So I short 1 to 7. And then I have a different plug for a EL41. So the same socket, but then a different plug that I just plug in. It's easier done than explained. But I would have a different plug for each type of tube. And because there's so few tubes, that's probably going to be easiest to do. What I'm looking for is actually a socket and plug system that has at least 15 pins, and that fits easily. I got one set which is very, very difficult, which is this over here. This is 12. 1, 2, 3. Yeah, 12. That's not enough. But this would be the male, this would be the plug, and the socket would be the one that will be permanently on there. And then I could just do the respective connections and plug this in for an L84, have a different one that I would label 12AX7, and so on and so forth. The problem is that pulling this out is very stiff. So this type of plug-in socket is not going to work. I'll find it. I'll find the right one. I can always revert back to the manual system, but we'll see how that goes. Okay. So here we have it. We switched it on. I've switched it on now. And actually, this is a bonus I did not expect. This thing, this neon is coming on, which is strange because there's no, this is just literally the 200 and, well, the B1 plus and B2 plus being switched through there. And it's still activating the neon. I don't know how they've wired the neon on there. But what we have here, if I look at the Funke card, it tells us that B1 plus is 200 volts, B2 plus, they call it UA and UG2. G2 is grid 2, so that's a screen grid, is 100 volts. And then they tell us that you bring the grid voltage to 0 and -2. Now the -2, I believe, is to give you your, to make sure that there's actually a transconductance going on, that there's an alteration going on. So we'll do that. We'll set this to 200 volts. Remember, this is tube stuff, so, half a volt here and there makes no difference. This is already set to an adjusted amount, and at the moment, because I'd played with this before, when that's 200, that's 100. Okay. Now we are looking at a negative bias of 27.5 volts. Our tube is in there. It's glowing, so our heater is already operational since I switched it on, really. And I've got 0 milliamps coming through because I've got no high voltage going on to there. Now, if I bring this down, the grid voltage is dropping, but because I've got no B+, I should still get no current. Now, if I push this down, switch it on, I can now watch that, and I bring this from -13, -8, it's starting to conduct. At 5.7, it's starting to conduct. See that? There's our -2 volts. I do wish I had a dual point here. I might actually do this. I might wire this. Instead of wiring it for 0 to 200 and only getting me 1 decimal point, I might actually wire this for 0 to 20, because I don't think I need less more than -20 volt bias on any of the tubes that I'm using, and I would really like to have a little bit more resolution on here. But at -2 volts, I've got 17 milliamps, and then if I go down to 0 volts, I've got 37. And the other thing I've noticed is this transformer, it's dropping a little bit, and that's because the reference, the minute you start drawing current, the voltage, that second, after that's on that second filter cap, does drop a little bit, and it does affect the reference Zenas, because the amount of current flowing through them drops a little bit. But anyway, there we go. I can always adjust this. I've got 38 milliamps, which is good. It's working. Now, if I do that, it goes away. I can switch it off there and take the high voltage away from there. So I'm back to my 200 and 100. Flick it on. Still no current because this is -13 volts bias. And if I start going down, this one's completely dead. No current. So this tube is bad, which is what I expected. I had a problem with that tube before and I replaced it. So that tube is bad. Okay. Switch that off. So here's another EL84 that I've got in there. It's an old tube. I'm not sure what condition it's on. 200 volts, 101, 21 negative. Let's give it high voltage and start bringing this down. Oh, it's starting to conduct. So 30. 30 is, where is it? It's just into the good on the chart that I've got there from the Funke card. And if I go to 2 volts, 2 volts, yeah. So if I've got -2 volts, I get 16. And if I've got 0, I've got 31. So that is 15 or 16 milliamps. So it's 8 milliamps per volt of difference, which is 8 milliamps per volt. It's supposed to be 11 milliamps per volt. But again, it depends on where on the curve you are. So this is a fairly weak tube. It's not that strong, but we can still look at the difference and know that it's sort of working. Okay. Increase the bias, cut the tube off, switch it off. So where does that leave me with this tester so far? So far, I'm happy with the metering circuit. I'm happy with the solution that I know that I have for switching on the meters. I'm actually very happy with the meters. I may make this more a resolution, so I may decide that I never want more than 20 volts negative bias, so I can make this 0 to 20. Instead of 0 to 200, I would have 2 decimal points of resolution. I think I'm going to try that. This thing this thing is measuring up to 200 milliamps at the moment. Now, if I test an ECC85, 12AX7, you know, the maximum current is going to be 1 point something milliamps. I can change the resolution on that, and I'm going to experiment with that and set that up with a toggle switch on here. So I would have higher current or lower current, more resolution again, and that's why that hole is already there. And I'm not sure that I want to change this switch. I like this one. I like this one. This particular one that I had here, this one is just far too stiff. And you have to hold it all the time, blah, blah. I don't think I like that one. I'll keep this one. And then I'm going to work out the best way to get the reconnecting for different tubes. And I think the next time I come back to you, I'll probably have the final board done. I'll have the switching for the supplies, the meters done, and probably some more information on more functionality than that I can get on here. I want to try, you know, be able to input a signal and see what the actual mu is, or what the actual S is going to be. In other words, how many milliamps per volt with an actual AC signal. It's not difficult to build a small, you know, 1 volt peak to peak 1 kilohertz signal generator and then measure the output. But I'm not sure if I want to do that. I'll have to think about this. As you probably have gathered, this is a work in progress, and I'll just adjust it as I go along. I want to see about the testing of shorts, find out if there's an easy way to do the shorts testing without going too far. Yeah, okay, I'm going to leave this for now because I've got a lot of thinking to do. But I hope that this thing proves to you that I haven't given up on this project. I've certainly spent enough money on meters, and I'm having a lot of fun with these experiments, believe me. I really like this phase of the prototyping. It's interesting, and you get a few surprises and a few discoveries, which always makes this more pleasant. So, hope you're enjoying this so far, and hope this is inspiring you. I know it's inspired at least one of you who sent me pictures of his. And all that remains for me to thank you for your company and tell you that if you want to support the channel directly, you can do so on Patreon and on PayPal. Links are in the description below. And thanks for watching. Bye for now, and stay safe.